Okay, we're now live here in C period on Thursday, February 25th. We're going to be covering the second half of section 6.2, which is on the indefinite integral anti-differentiation using substitution. So we'll begin with page 4, and you may hear some student chatter. C period, which is a very mild-mannered class, so I think this will go okay. Okay, so for example 6, we have this, right? 3dx over cosine squared 5x. We could probably write it like that. So you're going to want to rewrite the definite integral first. So you guys see why I did that? Remember, it's 1 over cosine squared, which we know is secant squared. Now, why is that advantageous? Like, why is it good to have secant squared 5x? Do we know what the antiderivative of secant squared is? Yeah. What is it? Tangent x. So this will make life a little easier for us if we do it this way. But before I get too carried away with doing the antiderivative, we do have that 5x, which creates a little bit of a problem. So let's let u equal 5x. If we do that, then du of dx, of course, is 5. And we can simply do a little algebraic manipulation. So dx is du over 5. Okay, so now we come back to our definite integral. It's 3 times secant squared. Now we're going to say u times du over 5. So this will be easier to take the antiderivative, because again, derivative of tangent x is secant squared x. Go ahead, Savannah.
Why don't we move the 3 outside of the integral?
So the question was, why don't we move the 3 outside the integral? Actually, we will. I just didn't feel like doing it. We will. So now, I'll package it with the 5 on the bottom. And whether you want to put the parentheses around u or not doesn't really matter. Just by habit, I just like to put as many parentheses as I like to. Again, as I mentioned about a minute ago, we know the antiderivative of secant squared x is tangent x, right? Because the derivative of tangent x is secant squared x. So now, I just do my antiderivative. And then I bring the 5x back in. So this is how I'd use substitution to evaluate the indefinite integral of 3dx over cosine squared 5x. If you wanted to check your work, if you took the derivative, so always a good idea to kind of quickly check your work. So 3/5 times secant squared 5x times 5, those cancel. And of course, that will get us 3 over cosine squared 5x. So we know that by checking it would work out. Go ahead, Jack Pleasance.
Could you do,
There's 2 Jacks in here. So.
would an alternative way work, like if you just, when you're taking the antiderivative of secant squared 5x, you multiply by, like, you do tan 5x times 1 over 5, because you're taking...
Right. So what Jack had mentioned as an alternative, which actually I'll just create a new screen. So we have 3 secant squared 5x times dx. Instead of going through the whole trouble of the u substitution, we know it's 3 tan 5x. And because the inside here was 5x, we know we're going to divide by 5. when you see enough of this, you kind of start realizing that's what we're going to do. So sure, yeah.
So kind of whichever way the problem.
Yeah, because it is a composite function. We have a function within a function. 5x is a linear term. It's inside a trig function. So we took the antiderivative of secant squared, which is tan x. But because it's 5x, we have to do some sort of, it's kind of like a chain rule kind of situation. So instead of going through the formality of the whole u substitution, as we see over here, we could just divide. Yeah, and that's something you'll see often. But we'll get to a point where, like, why do we keep doing this? Let's just do that.
Easiest for the problem.
Right. So the next one's going to be a little bit more challenging. You're going to want to use a trig identity. Now, I'm trying to think what's the best way to approach this one. You guys might remember, let's switch colors. You guys remember that, right? Okay. And what if I divided everything by cosine squared? So it'd be 1, sorry, tangent squared x plus 1 equals secant squared x. So you're going to have to use some of those Pythagorean trig identities. I'll give you some hints just so you're not lost.
Or would there
I don't know.
Yeah.
I'll think about it. Maybe not quite like that. That's a little crazy. I don't know. But so in this case, if I move things around, tangent squared x equals secant squared x minus 1. We already did the antiderivative of secant squared x in the previous example. So I think we're okay there. And the antiderivative of 1, of course, is just, no, antiderivative is x. So don't worry, I won't call your name for being wrong. Okay. So anyway, that was mean, I'm sorry. So anyway, so it's secant squared 5x minus 1 times dx. Okay. So we're replacing tan squared 5x using the Pythagorean trig identity. And remember, we're not doing x is our angle is 5x. And instead of actually doing the u substitution, we already know what the answer is from the previous example, right? I mean, we already know the answer is secant squared 5x. That's just going to be tangent 5x over 5 minus x plus c. So we didn't have to use u substitution because we already could rely on the previous example. There was a 3 in the previous example. I'm not going to use that 3. Actually, I'm glad you brought that up. Good, you redeemed yourself. No, I gotta stop it. I'm sorry. So, yeah, there was a 3 in the previous part. So, right, I might have confused you guys. We're not exactly using example 6. Well, it's 2 example 6. I just realized that. That actually should be. What should that be? Okay, this actually should be example 7, what we just did. So we'll just renumber them as we go along. So the example 6 previously had a 3. We weren't using that. It's just, you know, you're basically taking antiderivative of secant squared 5x, which you know is tangent 5x over 5. So, okay. You could check if you like, but, you know, you'll have to go back and then use the identity again to resubstitute. Go ahead.
So for like the parentheses on secant squared 5x minus 1, why are there parentheses around that but not parentheses around like tans or like sines?
You could.
Okay.
You could. I do it for secant squared 5x minus 1 because then it seems a little confusing. Are you taking the antiderivative of 1 or secant, you know, you want to show you're taking the antiderivative of the whole thing. So, all right. So again, you see there is a little bit of creativity needed for doing antiderivatives of trig functions. So it's not just doing a u substitution, but also substituting using identities. For example 7, we don't really know what the antiderivative tangent is. Because if you think backwards, the derivative of some function is tangent, I don't know, right? But what identity do you think we can use for tangent? That we, sine over cosine, right? So remember, tangent theta is sine theta over cosine theta. So that's what I'm going to do here. I'm going to push the 2 out to the left because it's a constant. That's always a good habit. Sine 6x over cosine 6x. No, no. Actually, well, I don't know. There's not really a quotient rule for antiderivatives, but we're going to use a u substitution. I wouldn't let u equal 6. You said let u equal 6x? Yeah. We're going to do more than that. What I'm going to do, I'm going to let u, and it's not going to be painfully obvious right now, but it will be when you see the solution, and then you'll see a consistency with other problems similar to this. We're going to let u equal cosine 6x. The reason why, that'd be great. Thank you. The door's going to be closed by Jack Burlinson. All right. Why? Because what's going to happen is that you're going to wind up getting something kind of like this. What is that going to be? We talked about yesterday. Yeah, the natural log of the absolute value of u. So that's why I chose to let the denominator equal u, because the hope is that if that's all I have left, I want to get something to look kind of like this. We want something like this, because then it's easy to take the antiderivative. We know the formula is just natural log of absolute value of u. So that's why I chose u to be cosine 6x. It's not painfully obvious in the beginning. It will be when you go through the problem, and when you see more problems like this, use that technique, you'll find it'll be more efficient. So I'm going to open a new screen because we're going to need more space. Go ahead, Stephanie.
Do you always put u as the bottom part of the fraction?
Usually, yeah, usually if you can. Savannah, go ahead.
How do you decide what to do, like what to make u, like what value?
Well, here's the other reason why too. If you take the derivative of cosine, what's the derivative of cosine? And we have a sign in the problem. So it's going to go away.
So do you just have to like think about it?
Yeah. Yeah, it's going to take some time. Yeah, and we're going to really spend a lot of time on this over the next few days. So let me go back. Let me go over here. So we rewrite the problem. It's 2 sine 6x over cosine 6x times dx. We're letting u equal cosine 6x. Of course, the derivative of that is negative sine 6x times 6, right? If you move things around, you should get du over 6, and we can push the negative to the other side. So if you see you can see the manipulations I made. I divide both sides by 6, multiply both sides by dx, and divide both sides by -1, or multiply both sides by -1, same thing. So I moved 3 things around, the dx, a 6, and a negative symbol, to transform the equation in that manner. Yeah, it's a 6x, yeah. Let me make that a little more neat. So that means that if I rewrite my integral, and again, when you get really good at this, you don't have to be as detailed to steps. You can kind of start substituting really quickly. But I'm going to deliberately separate things so it's easy to see that, oh, I can now just do 2 integral 1 over u. And all this is just negative d over x. Sorry, negative d over 6. So now I'm going to have negative 1/3 as my constant, and I'm integrating 1 over u times du, which is negative 1/3 times natural log of absolute value of u plus c. And of course, oh, because we replace sine 6x times dx with negative du over 6. And 2 and 1/6, 2 and 1/6 and a negative became negative 1/3. And if I replace u with cosine 6x, that's going to be the true antiderivative for tangent of 2 tangent 6x. Okay, this is good. We probably won't do page 6 because class ends about 13 minutes, but I think we could do page 5 for sure. Any questions so far? No? All right. So let's go back. And we see that 9 and 10 look very similar. 9 is 18x over x squared plus 9 times dx, but 10 doesn't have the x in the numerator. So of course they're going to have different answers, but they look very similar. But we're going to see that the way we go about our substitution is going to have to be a bit careful. So let's go with green. What do you think we should let u equal? Given that we need to somehow substitute for the other stuff. Good. Usually, I did say it's good to let the denominator equal u, but also, as a rule of thumb, allow u to equal denominator and or expression with the higher exponent. The reason why is because when you take the derivative of something with the higher exponent, guess what? It's now going to equal something with the lower exponent. And then you can substitute, and it becomes clean. So that's usually the rule of thumb, is allow u to equal the denominator and or, now in this case we got lucky that it worked for both, because when you let it equal the denominator, then you can take the antiderivative and get a natural log of something, right? Because the antiderivative of 1 over x is natural log of absolute value of x. So by doing that, what's du over dx going to equal? 2x. And if I move things around, du equals 2x times dx. And I could probably divide both sides by 2. Because now we see an opportunity to get rid of that x dx. X dx is going to be replaced with what? Du over 2. Mm-hmm. So now my integral can be written in this manner. I'm going to push the 18 out. This is constant. I'm going to write this as 1 over x squared plus 9 times x times dx. So just like what we did in the previous problem, yeah, 1 over u times d over 2. Because we know what x times dx equals, so we just do a swap. So 18 and 2 cancel. It's 9 times natural log of u plus c, which of course is 9 times natural log of the absolute value of x squared plus 9. Which actually, we don't really need the absolute value because x squared plus 9 will never be negative, but just by habit, I'll keep it there. And so that's your antiderivative of example 9. Any questions? Nope. Yeah, you guys have a chance to practice this tonight. Or for G peers watching this video over the weekend. Okay, example 10. What do you guys think? I mean, if I use u sub c, I'm not going to do the same technique, right? You can't let equal x squared plus 9, since we'll be stuck with an extra x, right? Because remember, when I took derivative x squared plus 9, I got 2x, but I was able to substitute that for example 9. How am I going to do that for example 10? The whole point is to make it easier to substitute. So, what do you guys think? If y equals, what's y prime going to be? Inverse of x, right? Isn't that kind of roughly the same structure? A little bit. So we'll have to get a little bit creative here. This is a little tricky, so I'm going to have to use a new sheet. So integral of 18 over x squared plus 9 times dx. Before I do the u substitution, actually I'm not sure if we're going to be using a u substitution, not 100% sure yet, but I'm going to write it like this. And then off to the side here, this is really wacky. Oh, I guess is the door locked? Oh.
I don't know if it's locked or just weak.
Yeah, I think you're weak. I'm just kidding. No, so it probably was locked because I didn't teach first period. No. Actually, it gets stuck. Okay, if I do that, notice how it becomes 1/9 over x squared over 9 plus 1. That's the same thing as 1 over x squared plus 9, right? Because I just multiplied. Why am I doing that? Because then I can utilize this technique. Maybe not. This is a little too much, I think. So dy over du equals inverse tan of u when you have 1 over u squared plus, or 1 over any variable squared. The variables are arbitrary, right? But so there's definitely some creative algebra happening here. So 1/9 for x squared over 9 plus 1 times dx. So I just rewrote that fraction. And the 1/9 is a constant, so actually I can, what's 18 times 1/9? Yeah, so I could just rewrite it like that. Excuse me. So now in this case, hold on a sec. Just hope I didn't confuse myself here. If we yeah, now I'm good. Okay, I just got a little bit confused, but now I'm good. X squared over 9, of course, is x over 3 squared, right? Okay. Yeah, I don't think you guys would think to do this, but hopefully you can at least follow the algebra. So there's a lot of transformations, substitutions, stuff like that. Now I'm going to use the U sub. Yeah, I'm going to let u equal x over 3. Meaning that du over dx is 1/3. And by moving things around, or cross multiplying, 3 du equals dx. And we can see that fraction 1 over parentheses x plus 3 squared plus 1 represents, yeah, exactly. Yeah, this is wild. So it's 2, 1 over u squared plus 1 times 3 du, which is 6 integral 1 over u squared plus 1 times du. Now I can actually take the antiderivative. 6 times inverse tan of u plus c. Or 6 times inverse tan. That's one I get this problem over with. I don't like it anymore. So we had to change up the fraction. It was, yeah, it's a really, this is definitely a tough problem. Yeah, I don't think we'll put us on a test. I don't know. I haven't decided yet, but. It's,
I know for sure I
Can
would
you
not be
explain
good at
how you
that.
went through the whole process again?
yeah, let me recap it. But Jack, go ahead. You have a question?
So is there a rule of thumb for when we would know not to do like because we didn't want to do the set u equal to the denominator and the highest power this time? Is
Right.
that because there was no like last time the power was 1 order away.
Right, right, because you don't have another term that's 1 order away from x squared plus 9. That's why we wouldn't want to let u equal x squared plus 9.
So it has to be 1 order away.
Right. Okay, if you guys can just quiet down 1 sec, we've got about a minute and a half left. Okay, exactly a minute left. So just really quickly, we had this. I recognize that it kind of looks like the derivative inverse tan of u, but I had to prep it, so I pulled the 18 out, so I get the numerator as 1, which is great. But then I have to get the number being added to x squared to be 1, so I multiply top and bottom by 1/9. Then, when I have 1/9 in the numerator, I just multiply 18, get back to 1, it's 2. But then x squared over 9, I convert it to x over 3 squared, and let u equal x over 3, and then did my integration. And so that covers it.